Hi, welcome to Management Science 291. What's the point of statistics? Statistics is the study of the collection, organization, analysis, interpretation, and presentation of data. In Stat 206, you focused on the analysis, some t-tests, some simple linear regression, and a few other methods. We want to provide meaningful information in an easily accessible way. We want to process data, that is information, so that it is useful. And we want to use it to answer questions. Now, statistics is a science, and it also is an art. So this semester you'll be learning the science behind statistics and hopefully pick up on the themes that require a little bit of your creative side. I keep saying that the sexy job in the next 10 years will be statisticians, and I'm not kidding. A quote from Hal Varian, chief economist at Google. So you'll find lots of articles touting the profession of statisticians. There are lots of jobs open. Notice here that when I pulled up this page on data and analytics positions at Facebook, there are 164 open positions. And this is a banner that scrolls through when you do this search for Facebook. And I stopped it on this quote by Rick M. Quote, "If there's no set solution for your problem, you hack it and solve it yourself," unquote. So it sounds like Rick M. has gotten the idea behind working with finding patterns in data. Sounds like they process an awful lot of data at Facebook, and he has tapped into that artistic side. He has figured out that you've got to be creative sometimes. You need to know the science, but you also need to be able to be creative. And I'm going to ask you to be creative this semester. We're going to give you challenges, especially with those case studies and projects, and you're going to need to sometimes think outside the box to get your answer. Okay, so it says, at Facebook, we leverage data for good. Every piece of data helps us understand Facebook's products and growth, identify opportunities, and execute ideas at a global scale. We're able to make smarter, more informed decisions and develop better products that maximize our impact to bring the world closer together. So every industry uses statistics, every single industry. So statistics is a good set of skills to know, because you are probably going to encounter it. There's a 99.9% chance that you're going to be encountering it when you get out of this class, and will probably be asked to do something that you've learned in this class. Okay, also the best 11 jobs in America for 2017. I just did a little Google search and noticed that data scientist here is number 1. And the average salary is $110,000. So it's a very good career if you are ever thinking about switching your major, or some of you may already be interested in data science. Okay, so the goal of this class is to develop a practical, real-world approach to using statistics. We're going to understand the data, so explore the data, then decide on which appropriate statistical tool to use, and then communicate the insights. So this semester, there's a lot of emphasis on the applied part, understanding what the data means and what you can do with it. We are not going to worry too much with theory or background calculations or proofs. We're going to try to give you a real-world emphasis on statistics. So in the first part of the semester, we're going to develop our toolkit, understanding data, visualizing data, cognitive bias, and how that can affect our summaries, and then review of basic statistics. And then after exam 1, for exam 2, we're going to go back over hypothesis testing, ANOVA, and regression. You may not have learned about ANOVA previously, but we will teach you what you need to know. And so these are statistical tests so that we can test our ideas. And then in the third part of the semester, we're going to learn to make predictions through advanced regression, forecasting, and learn diagnostic tools. So chapter 3 in your textbook is data visualization. We follow along with your textbook this semester, but I have added a material that I feel I know is important. So when you're reading along with the chapters, just keep in mind that I will be introducing other things that your textbook doesn't in certain places. Okay, so condensing data helps, especially visually. So we have qualitative data and quantitative data. So remember, quantitative data is a quantity. So those are numerical data sets. So you get a data set of numbers where it makes sense to take the average or do a calculation on them. Take an average, do a sum, do a median, something like that. Qualitative data is qualities. So the word that comes out of there is quality. And that's when you're putting things into categories. All right, and then nominal and ordinal in the qualitative data is, nominal is just the name of a category, and ordinal is when those categories have some sort of natural ordering. Just a little review of what you've learned in the previous semester. And then the quantitative data, remember, is when you get a data set of numbers, but it makes sense to take the average, do a calculation on them. All right, so we can categorize or group our responses doing frequency distributions. And then when we want to visualize the data with a graph, it matters whether we have qualitative data or quantitative data. So for qualitative data, we might do a pie chart or a bar chart. And for quantitative data, we might do something like a histogram, a Boxplot, Polygon, or Ogive. So we're going to go over some of those now. The first plot we're going to talk about is the stem plot, otherwise known as the stem and leaf display. So this is for quantitative data, so a numerical data set, and it works for small to medium data sets. Now you're not going to see these as much, but we're still going to go over it because you may see them. The stems on a stem plot are the core values of the data, and the leaves are the last values of the data points. So we're going to put the leaves in numerical order. I'm never going to do one without them in numerical order. I think it's just better to put them in order. Something that you should make sure you pay attention to is to never put punctuation between the values. We don't want to see decimal points or commas or any kind of punctuation in our graphical display. And remember that a stem plot should always include a key with units. So we have an example. The PE ratio, which is stock price divided by earnings per share. So the price earnings ratio. These are quantitative and continuous data, but rounded to whole numbers for convenience. So the following is a sample of 44 of these ratios. So let's take a look at this data. Notice that we have 7 is our lowest value, and let's just pick out another one to look at on our stem plot, the number 11. There are 3 of them. So let's pay attention to those 4 values on our actual stem and leaf plot. So on an actual stem and leaf plot in a publication, you wouldn't have any of this over here. Okay, so this thing is your stem and leaf plot. And usually the stem goes closer to the leaves, but I took this one from your textbook. I wasn't going to take time to make my own stem and leaf plot because they're just not used that much. So this is a good enough example for us to get started with. So remember I said to pay attention to that observation of a 7. Where is that on the stem and leaf plot? Well, here we can see that our stems are the tens digit in our values. And so 7 is right here. It has a stem of a 0 and 7 as the leaf. And then where's 11? Well, it has a 1 in the tens spot and a 1 for the leaf, and it was repeated 3 times. So that 1 with the 3 ones after it denotes our 3 11s in our data set. And technically this should have a key with units. So this was price earnings ratio, stock price over earnings per share. So we would usually want to put something here that says something like key. And I would say maybe 0 bar 7, because lots of times when you look at a stem and leaf plot, there'll be a vertical bar here. And then you say means whatever it means. And that's where you get to put your units. That way people know if it's some kind of, this without a label on this, this could be 0.7 pounds, right? 0 bar 7 could be 0.7 pounds. We have no idea what the context is unless you've got a key. All All right, and then a dot plot. That's similar to a stem plot, only it's turned horizontally with the dots replacing the leaves. So I think you all know what a dot plot is. So let's look for our 311s. We can see them right here. So this is 10, 12, 14, 16, 18, 20, and number 11 is right here. So this is our 311s, those 3 dots. And that was for our same data set that we were working with before. Okay, so now onto a graphical display you're actually going to see quite a bit of, and that's a box plot. So a box plot displays, again, quantitative data. So when you've got one of those numerical data sets, and that's what we'll mostly be working with this semester. This works for small to large data sets. It can work for even very large data sets. It is a plot of the 5-number summary. So remember that bottom whisker on your box plot goes down to the minimum. The bottom of the box is your first quartile, that is the place in the distribution that has 25% below it. The top of the box is your third quartile, that is the place in the distribution that has 3/4 below it, or 1/4 above it. The line that divides the box into 2 parts, is the median, otherwise known as Q2. So you could either call that the median or Q2. And then the top whisker here doesn't go quite all the way to the maximum of the data set because we have outliers. So we're going to use R, remember, this semester. And so the top of our whisker in R is just going to go to the last observation before the upper fence, before that cutoff for outliers. And then these dots are all outliers. And so, of course, that top dot is the max. So R is going to automatically do that 1.5 times the interquartile range rule to calculate outliers, and it's going to plot the outliers separately from the top of the whisker, or the bottom of the whisker if you've got outliers in the bottom end of the distribution. Now, what are box plots good for? Well, they can do any size quantitative data set, but what really makes them good, because we've got other options, we've got a histogram, but what really makes a box plot good is that we can compare quantitative distributions on some kind of categorical variable. So notice that this data set was single family home sales. What if I wanted to break that up across regions? So here, we've taken that data set, we've broken it across the central, northeast, west, and southeast regions. Now we can really see what was driving those high home sales that created those outliers. We can see that in the west, we've got some really high home prices. The distribution of home prices for the west is shifted up from central, northeast, and southeast. We can also see there's more variability in the west in home prices. So the box plot is really great when you want to compare a quantitative variable across different categories. The histogram is another great graphical display for quantitative data. So again, I've graphed the single family home sales. Here I've used Excel to make this graph. We have the home sales, the number of sales on the vertical axis, and on the horizontal axis here we have the actual home prices. So remember those really high home prices up in the 700,000s range? Those are graphed up here on the histogram. The height of the bar tells me how many home prices in the data set were in that category. So less than 10, less than 5 even. We can see that most homes were here between $81,000 and $168,000. So the histogram, remember, the height of the bar can represent the number of observations in a certain category, or it can denote the percent of observations in a category. So this one is called a frequency histogram because it denotes the number of observations in a category. But if I changed my vertical axis to the percent of sales in a category, it would be called a relative frequency histogram. Now on this frequency histogram, what do the heights of the bars add up to? Well, this one represents the number of homes in this category, the number of homes in this category, the number of homes in this category, etc. So we're putting every home in a category. So the height of the bars here add up to the number of observations in your data set, your sample size. In a relative frequency histogram, this would represent the percentages. So this would be like 78%, this would be 35%. Of course, this isn't relative frequency, because what should the heights of the bars add up to in a relative frequency histogram? Well, since it's the percent or proportion of observations in each category, it's going to add up to either 100 for a percent or 1 for proportion. Okay, so this was going to be a clicker question if we had class. So I'm going to give you a second. You might want to pause this because I'm going to go ahead and tell you the answer to this question in just a second. So try to figure it out on your own and pause me. The shape of this distribution is A, skewed left, B, skewed right, C, symmetric, or D, bimodal. All right, here comes the answer. So remember that the direction of the tail is the skew. So here we have, if we overlaid it with a smooth curve, and this was some kind of an animal, the tail goes this way. It goes to the right. So this one is a skewed right distribution. Now don't feel bad if you got that wrong, because this is a common place for students to get the language confused, turned around backwards in statistics. Just find a way to remember it. So another way that you can remember which way a skew goes is if you think about like the normal distribution, a unimodal symmetric curve. If we split that in half, the right side, if your graph looks like the right side of the normal distribution, then you have a skewed right distribution. If your graph looks like the left side of the normal distribution, then you have a skewed left distribution. So that's the way you remember which way a skew goes. Now, comparing the box plot to the histogram. So I said that the box plot and the histogram both can graph very large quantitative data sets. How do we choose which one we want to use? Well, the histogram can display the same kind of data set as a box plot. They can both display the same kind of data set. However, the histogram shows more detail about the shape of the distribution. Here, with the box plot, we don't know if maybe there are two modes in our data. We don't know if there are two lumps in our data. When we have the histogram, we can clearly see that this is a unimodal distribution and it's skewed right. So the box plot hides certain features about the shape of a distribution. So it loses out when you're thinking about wanting to know the exact details of a shape of a distribution. But the box plot is better when we want to break our quantitative variable across some categories. So remember, the box plot is better when you want to compare side-by-side distributions of a quantitative variable across categories. And the histogram's better. It's not very good for side-by-side comparisons, but it's better when you want to show the features of the shape of the distribution. So we've got lots of shapes of distributions. We're just going to give you a couple basics for the language to talk about this semester. Of course, we've already talked about skewed left, symmetric data sets, and skewed right. Remember, symmetric is when you just have a line of symmetry. So underneath that is another symmetric data set. This one's symmetric. That left side is a mirror image of the right side. But here, in the top graph, this one's unimodal. It only has one peak in the data. And this one is multimodal. So if we have two bumps in the data, like this one here, we call that bimodal when it has two lumps in the data, because bimodal data sets are very, very common. Now your book says this is bimodal and skewed left, but in practice we don't call that skewed left. We would say it's bimodal with one mode around whatever value this is and another mode around whatever value this is. And we would say a smaller mode around this value because that has shorter bars. And same with this one over here on the right. we would say that's bimodal with one mode here and a smaller mode in there. And of course on the bottom we have skewed left with outliers, symmetric with outliers, and skewed right with outliers. So that basic language will get you through lots of the pictures that you'll find in practice. Something that you're not going to see quite as much is frequency polygons and ogives. So a frequency polygon is a line graph that connects the midpoints of the histogram intervals plus extra intervals at the beginning and end so the line will touch the x-axis. Pure statisticians do not use frequency polygons and ogives very much. This serves the same purpose as a histogram, but the reason that it's used is when you want to compare two data sets. Remember we said the histogram was not very good at comparing two data sets. So this one allows you to compare two data sets because it's easier to overlay like these two line graphs than it is to overlay two histograms. And then an ogive is a line graph, so it's over here on the right, is a line graph of the cumulative frequencies. It's useful for finding percentiles or in comparing the shape of the sample. Okay, and then a line graph, something you're going to see a lot of, very frequently. So this displays a quantitative variable again, changing over time. Time should go on the horizontal axis, that is on the bottom, on the x-axis, and the variable should go on the vertical axis, otherwise known as the y-axis. And we can use different lines to denote separate categories or groups. So I downloaded some data from the Bureau of Labor Statistics, bls.gov, on unemployment. And this goes through the year mid-year 2014, this data set. So my variable on my vertical axis is unemployment rate in a percent. And then my time, remember, goes on that x-axis, that horizontal axis. So notice that I've got 4 lines on here. I could have just done the overall unemployment rate, but I went ahead and broke it down by different categories. So we notice this blue line on the bottom is for bachelor's degrees or higher. The second line is some college. The third line is for those that only have a high school diploma. And the top line is for those who have less than a high school diploma. All right, so why did I bring this in as an example of how to do a line graph with different lines on it? Because it's also educational. I thought it was very striking, this pattern, that those who have less than a high school degree, so everybody felt the pinch in 2009 when the economy crashed, right? Unemployment went way up. So there was an increase in unemployment across all categories, and then things started to get a little bit better as time went on. Unemployment's decreasing for each category, for all categories. So they all have the same pattern. However, the unemployment is always higher over these periods as you move to a lower degree. Or another way to look at it is unemployment is always lower as you get higher in a degree. So staying in college looks like it's definitely the best way to go. Unemployment is always lower across all these time periods as you have a higher degree. All right, so you'll see these kind of examples. This one's in your textbook, and I'm going to tell you to beware of plotting different scales. Sometimes it can make your mind just jump to drawing some kind of a conclusion that you really shouldn't be drawing. So here we've got one scale on the left, which is for the red line, or nope, it's for the blue line, average monthly bill in dollars per month. And over here on the right, they've overlaid another scale, which is minutes per call for a call length, and that's the red line. And we can see the different, which line goes with which by the key here. So we have the red line with the squares on it is the average call length, and the blue line with the circles on it is the average monthly bill. Now, why would I put these squares and circles on this when I already have colors indicating the lines? Why did I do a different shape for the dots? Think about someone who's colorblind. This is something that you really want to give some thought to when you're making graphical displays. Someone who's colorblind may not be able to see which one's red and which one's blue, And so the shapes will help somebody who's visually impaired in some way be able to determine which line goes with which key. So you always want to keep in mind that not everyone can see the same colors or shapes that you can. So you can overlay two different scales on one graph, but I recommend against it. If you've got room, I would plot them separately unless you're trying to make some kind of a direct comparison of the patterns. It's hard to make a direct comparison of patterns when you have two different scales, because if I change the scale over here to 10, to dividing everything by 10, it could totally change the way that that this pattern looks on the visual, on the graphical display. So it can really distort things. So I just recommend against it. All right, so now we're going to get into some graphical displays for qualitative data, or otherwise known as categorical data. So we're going to talk about a bar chart first. This can be horizontal or vertical. Now your book makes a distinction. They call a horizontal bar chart one thing and a vertical bar chart this another thing. And I think Excel does too, in older versions of Excel. In practice, we do not care whether a bar chart's horizontal or vertical. There's no need to come up with an extra name for something. We call them all bar charts. So bar charts can display parts of a whole or separate values. So here's an example of a bar chart where we are plotting separate values. These are not parts of a whole. So I got this data. I've put the reference at the top of the graph. This is U.S. government tax revenue as a percentage of the gross domestic product for 8 countries who are part of the Organization for Economic Cooperation and Development. So yeah, it's government tax revenue. All right, so for these countries. So on my vertical axis, the height of the bars represents the tax revenue as a percent of gross domestic product. And on my horizontal axis, I've got my countries. So a bar chart looks an awful lot like a histogram, except what? The bars do not touch, because these are just categories. They're not adjacent categories of numerical values. These are just name categories. All right, so it's easy to see what this represents. Canada is about 30%. France is about 45%. It's easy to see what the heights of the bars represent. But we can already improve on this graph. So there's usually a way to improve on a graph. When I ask you to make a graphical display, I want you to be very, very careful and put a lot of thought into how you present your information. So this graph will be fine. It gives the information. It's okay. It has labels on my x-axis and my y-axis, and it's easy to read. It's easy to see. However, we can always improve. We can almost always improve on our graphical display. So on the next page, on the next slide, I've already done what I consider to be an improvement. Notice back here, it's kind of hard to see which one has the smallest tax revenue percent. And we can tell, but it's just more difficult to see. On this next graph, you can see that I've just reordered the categories so that we go from the highest to the lowest, or I could have gone from the lowest to the highest, whichever looked better in your publication, whichever looks better. And that allows for easier comparisons. Now we can clearly see that USA has the lowest and France has the highest. It's much easier to see when we put them in order, in decreasing or ascending order. Now here's another example. Here's another thing that I wanted to emphasize on this, is that it's an example of how you can turn a bar chart on its side. This would have been perfectly fine to stand the bars vertically again like the previous display did, but I decided to put these on the side because I thought it looked nice. And it's all depends on how it lays out in your publication. Sometimes it's better to do it vertically, sometimes it's better to do it horizontally, and sometimes it doesn't matter. So the same information, we just ordered those categories. Now, if these categories were an ordinal variable, then we might order them by the actual categories themselves and not the amount that the category is representing. So that's another thing to consider. Okay, so other kinds of bar charts that you're going to run into. I got these next three from Pew Research. They do a lot of surveys, and so they have a lot of bar charts because you get a lot of categorical responses when you're doing surveys. So this one's just an example of what we call a stacked bar chart, or sometimes it's called segmented. Again, it can be vertical or horizontal, and here they can put two categorical variables. Here their example is belief in God and generation. And why is it called stacked or segmented? Because we've stacked categories within another category. A side-by-side bar chart is the same idea as the segmented, but instead of stacking it this way, we put the subcategories side by side. So here, this one is the description of self and generation. And another one is the back-to-back bar chart. So here it was a survey across generations, racial differences in Obama job approval. So on this one, they were able to put three categorical variables: race, generation, and approval. So because this one category only had two levels, disapprove and approve, they could do the back-to-back bar chart. So it's kind of like a stacked, but we call it back-to-back because there's sort of a line that divides everything here. For the left side is disapprove and the right side's approve. And we were able to have generation and race. So three categorical variables. So there's all kinds of variations on bar charts. Just make sure that yours is clear and honest. All right, so we're going to get to the pie chart, otherwise known as a pie graph. This is also for categorical, otherwise known as qualitative data. It displays the parts of a whole. But pie charts are not good when there are too many categories. So here, this one's okay. Where did you buy your statistics textbook? On the internet, a retail outlet, from another student, or the campus bookstore. It has 4 categories. So it's done okay. In general, I know you're going to see a lot of pie charts, but there's a growing number of people that are very annoyed by the overuse of pie charts. In general, a bar chart is almost always better. A bar chart or bar graph can do everything a pie chart can and then some. So I could have a bar chart for this data where I have 4 bars, right? I can have the web, a retail outlet, a campus bookstore. I didn't go very well in order here, and another student, right? So I could have a bar chart, or I could put them in order too, from least to greatest to least, something like that. Yeah, we only have 4 categories. So my bar chart can represent all the parts of a whole, right? It can do everything this pie chart can, but it can also do more. Remember, it can also, the bar chart can also do those separate categories where you don't have all the parts of a whole. Like when you're just looking at those separate countries and their tax revenue. Or if you're looking at the average SAT score for an admitted freshman across several southern universities. Each bar would represent the average SAT score for a single university. And those numbers are not the parts of a whole, right? Okay. So a pie chart is used very frequently, but it's too easy to make them look bad and there are too many drawbacks. So we don't recommend using them if you have any more than like 3 to 5 categories. Also, they're terrible for comparisons. Notice that when we ordered our bar chart in the tax revenue example, it was great for comparing those categories. Look here at this set of pie charts that was taken from a cdc.gov data brief. And this is on the what is driving death rates for different age categories. So it's not good for categories. It's too hard for your eye to move from one pie chart to the other and have a separate legend for each one. And then it's difficult for our eyes to compare the areas when we have an angle involved. It's much easier for us to just compare the height of a bar than it is for us to look at the size of a slice of pie. Now, things that are done well on these side-by-side pie charts is that the color for each category is the same no matter which pie chart you're on. So accidents is always dark blue, no matter which age category you're in. And in this case, they've also put them in order from greatest to least. So the top one is always here on the top right, and as you move around, it gets smaller until you lump all the other categories together. Okay, so just take note that pie charts are annoying to some people in your audience, so definitely don't put more than one, maybe two in your presentation. If you're presenting data, try to use bar charts, and they're terrible for side-by-side comparisons. Okay, so jumping back to quantitative data, we have the scatter plot. So I'm going kind of quickly because I know you've all learned this in your previous stats classes, but I'm trying to fill in some other blanks as we talk about them. So a scatter plot is used to depict two potentially related variables. And this is when you have a quantitative X and a quantitative Y. So each point on a scatter plot is an XY coordinate. So you have how far you go over in the X direction and how far you go up in the Y direction. Tells you where a point goes. So our example is the relationship between education and income. So here we have years of education on the x-axis, on the horizontal axis, and income on the y-axis, the vertical axis. So we have one dot here where there's 2 years of education and a little bit less than 40,000 in income. So that's the way that you interpret the dots on a scatter plot. And what we do when we have a scatter plot is we look at the relationship between those two variables. Here, it looks like there's an increasing trend in general. As you have more years of education, you get higher income, which makes sense. And we've got this one point that's kind of not following that pattern because it would be probably down here if we were having a linear pattern. We'll talk about those different kinds of patterns when we get to our simple linear and multiple linear regression chapter. Notice over here on the right, these other scatter plots. This one is an increasing linear relationship, a positive linear relationship. Here it looks like we've got a positive curved relationship. And here it looks like there might be really no relationship between the X and the Y.